Hello everyone, welcome to new class. Today's class is about the electrical analogues of mechanical rotational systems. The three basic elements moment of inertia, rotational dashpot, and torsional spring that are used in modeling mechanical rotational systems are analogous to resistance. So, the moment of inertia, rotational dashpot, and torsional spring are analogous to resistance, inductance, and capacitance of electrical systems. The input torque in mechanical system is analogous to either voltage source or current source in electrical systems. The output angular velocity in mechanical rotational system is analogous to either current or voltage in an element in electrical system. Since the electrical systems has two types of inputs, either voltage source or current source, there are two types of analogies: torque voltage analogy and torque current analogy. So let us study about torque voltage analogy. So the torque balance equations of mechanical rotational elements and their analogous electrical elements in torque voltage analogy are shown in this table. So the torque, that is in mechanical rotation system, the input is torque and which is analogous to voltage source in electrical system. So in torque voltage analogy, the input is voltage source and output in mechanical rotation system is angular velocity, and which is analogous to current through the element in electrical system. In the case of dashpot, omega is the angular velocity, and that is d theta by dt, where theta is the angular displacement, and angular displacement in mechanical rotation system is analogous to the charge q in electrical system. And we have t is equal to b into d theta by dt, or we can write b into omega, because this angular velocity is the derivative of angular displacement, and this b is the rotational coefficient of dashpot, and that is analogous to resistance r, because here in this way t is the input, so here we can write e is equal to r into I. So in the case of electrical system, this resistance is analogous to the rotational coefficient of dashpot b. Next is mass. So in the case of mass element, alpha is the angular acceleration, and that is equal to d square theta by dt square, or we can write d omega by dt. That is, angular acceleration is the derivative of the angular velocity, or second derivative of the angular displacement. And here we can write t is equal to j into d square theta by dt square, or we can write j into d omega by dt, where j is the moment of inertia and which is analogous to inductance L in electrical system, because we can write E is equal to L into di by dt. Next is spring. So in the case of torsional spring, we can write theta is equal to integral omega dt. So here t is equal to k into theta, and that is equal to k into integral omega dt, where k is the stiffness of spring And in electrical system we can write E is equal to 1 by C integral I dt, where C is the capacitance. So this K is analogous to 1 by C. So in torque voltage analogy we can write torque is analogous to the voltage source. Then angular velocity omega is analogous to the current through the element. Then B, that is the rotational coefficient of dashpot B, is analogous to the resistance R. Then J, J is the moment of inertia, which is analogous to inductance L. Then the stiffness of spring K is analogous to reciprocal of capacitance C. And also theta, that is the angular displacement theta, is analogous to the charge Q. So this is in the case of torque voltage analogy. And the following points serve as guidelines to obtain electrical analogues of mechanical rotation systems based on torque voltage analogy. First one is, in electrical systems the elements in series will have same current. Likewise in mechanical systems the elements having same angular velocity are said to be in series. Second one, the elements having same angular velocity in mechanical system should have analogous same current in electrical analogous system. Third one, each node in mechanical system corresponds to a closed loop in electrical system. The moment of inertia of mass is considered as a node. Fourth one, the number of meshes in electrical analogous is same as that of the number of nodes in mechanical system. Hence, the number of mesh currents and system equations will be same as that of the number of angular velocities of nodes in mechanical system. Then fifth one, the mechanical driving sources and passive elements connected to the node in mechanical system should be represented by analogous element in a closed loop in analogous electrical system. Then sixth one, the element connected between two nodes in mechanical system is represented as a common element between two meshes in electrical analogous system. Next is torque current analogy. The torque balance equations of mechanical elements and their analogous electrical elements in torque current analogy are shown in this table. So here the input is torque and output is angular velocity, whereas in electrical system the input is current source and output is voltage across the element in torque current analogy. So the torque is analogous to current source and angular velocity omega is analogous to the voltage across the element. Next is, in the case of dashpot, we have omega is equal to d theta by dt, and t is equal to, that is the torque T is equal to B into d theta by dt, that is B into omega. And here in this manner we can write, that is torque is analogous to current, so I is equal to 1 by R into V, or we can write G into V, where G is the conductance. So B, that is the rotational frictional coefficient of dashpot, is analogous to the conductance G. Also here the angular displacement theta is analogous to the flux phi. In the case of spring element, we can write T is equal to K into theta, and that is equal to K into integral omega dt. In electrical system we can write I is equal to 1 by L into integral V dt. So here the stiffness of spring K is analogous to the reciprocal of inductance, that is 1 by L. Next is mass element. Here the angular displacement alpha. angular acceleration alpha is equal to d square theta by dt square, or we can write d omega by dt. So the torque T is equal to j into d square theta by dt square, and we can write j into d omega by dt, and this j is moment of inertia, which is analogous to the capacitance C in electrical system, because we can write I is equal to C into dV by dt. So these two are analogous. So J is analogous to capacitance C. So in torque current analogy, we can write torque is analogous to the current source. Then angular velocity omega is analogous to the voltage across the element. Theta is analogous to, that is, theta is the angular displacement, which is analogous to the flux phi. Then B is the rotational frictional coefficient of dashpot, which is analogous to the conductance G. Then K, stiffness of spring K is analogous to 1 by L. Then J is the moment of inertia, which is analogous to 1 C, that is the capacitance C. So this is in the case of torque current analogy. And the following points serve as guidelines to obtain electrical analogues of mechanical rotational systems based on torque current analogy. First one is, in electrical systems, the elements in parallel will have same voltage. Likewise, in mechanical systems, the elements having same torque are said to be in parallel. Second one is, the elements having same angular velocity in mechanical system should have analogous same voltage in electrical analogous system. Third one, each node in mechanical system corresponds to a node in electrical system. The moment of inertia of mass is considered as a node. Fourth one, the number of nodes in electrical analogous is same as that of the number of nodes in mechanical system. Hence, the number of node voltages and system equations will be same as that of the number of angular velocities of nodes in mechanical system. Then fifth one, the mechanical driving sources and passive elements connected to the node in mechanical system should be represented by analogous element connected to a node in analogous electrical system. Then sixth one, the element connected between two nodes in mechanical system is represented as a common element between two nodes in electrical analogous system. So this is about the torque current analogy and torque voltage analogy. So let us do the problems related to this torque current analogy and torque voltage analogy in the next classes. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.